for all. I am the Dr. Hani Boubekri, teacher research at Higher Normal School of Technological Education, SKIGDA, and member of the Research Laboratory of Laser Physics, Optical Spectroscopy, and Optoelectronics at the University of Annaba. I present to you my work entitled Dependence of Geodophyte Parameter Values with Orbium Concentration in Cadmium Fluoride Single Crystal Host. In recent years, our rare earth element doped host matrix have been studied extensively due to their potential applications in green technology. They have an important role in the development of optical systems, clean energy, infrared radiation detection, medical applications, optoelectronic devices, biological fluorescence labeling, laser technology, so they have been reported in various files. The purpose of this work is to investigate the optical properties of orbium ion doped CDF2 single crystals. For this reason, we are particularly interested in the orbium ions because they exhibit an intense red emission and also narrow transition in the absorption and diminution spectra, leading to the possible use as probe of the local environment. Furthermore, laser based on the red emission of orbium could also be an attractive choice for medical application since near-infrared radiation can penetrate biological tissue such as human skin. Also, the UV visible excitation of 5D0 orbium levels generate yellow, red, and green emission, leading to white light greatly required in many applications. For the experimental part of this work, we choose the fluoride materials. Among all solid-state laser materials, the fluoride have the advantage to be transparent in large electromagnetic domain, and they have low maximum phono frequency, leading to a large number of potential emitting levels by limiting the non-radiative emission. The fluoride crystals MF2 with fluoride structure are great interested as material for photonics. Doped with trivalent earth ion, they are the basic materials for many applications in laser technology. The CDF2 crystals occupy a specific place among these MF2 crystals. They are transparent in the near UV visible and infrared electromagnetic domain. CDF2 is used as main constituent of many fluoride glasses, material for laser array and infrared detector, and medium for optical information processing systems. Orbium ion doped CDF2 single crystal with different nominal concentration are ground by use of the Bridgman technique from vacuum furnace in fluoride atmosphere. After the purification steps, orbium ion were introduced in the form of trifluoride powders. The luminescence properties are studied by photoluminescence measurement conducted on a Parker-Nillmer spectrophotometer using xenon lamp as the excitation light source at room temperature. In the first, we have enregistered the excitation spectra at room temperature with different concentration of orbium ion. The excitation spectrum monitored by the emission at 585 nanometer corresponding to transition from the emitting level 5D0 to 7F1 emission and recorded between 200 and 550 nanometers. Many resolved peaks are observed and attributed to the transition from the ground state to the excitation one. We choose the most height transition corresponding to the transition between 5 F0 to 7 L6 transition to enregister the emission spectra for different concentration of orpium ion. The emission spectra for different concentration of orpium ion are monitored by the excitation at 385 nanometer and recorded on the Parkinilmer spectrophotometer between 450 and 700 nanometer range. Each spectrum exhibits three peaks positioned around 594, 614 and 650 nanometer, corresponding to transition from the emitting level 5D0 to the ground state 1, respectively. It is clearly observed that the emission corresponding to the 5D0 to 7F1 transition have the highest intensity in each spectrum. This transition is assumed as a reference transition because it is the only one allowed by the magnetic dipole mechanism. It is often considered to be constant and is used to calibrate the intensity of orpium luminescence spectra. On the contrary, the 5D0 to 7F2 electron dipole transition occurring in the red region is very sensitive to local environment and its intensity depends on the symmetry of the crystal field around the orpium ion. In accordance with other publications, it is established that the relation between these two transitions is influenced by the symmetry of the host lattice. To perform this study, the result of luminescence and lifetime measurement were analyzed. The Guido field intensities parameter were investigation used the data taken from the luminescence spectra, which allowed evaluating of the transition probability, radiative lifetime, and as final result emission cross-section and the quantum efficiency of the orpium in CDF2 single crystal. The Guido field model was developed to calculate the probability of radiative transition between the energy levels of the 4F configuration of orpium ion, which allowed us to access several spectroscopic parameters. This method depends on the quality of absorption band, which must be equal in number to Atlas 4V4. Very distinct transition to be able to perform the adjustment calculation by the least square technique. In the case of the nanopowders, there is no possibility of obtaining the absorption spectrum directly. In this case, the emission spectra will be used. It seems interesting to us to carry out this study on the CDF2 host matrix doped with orpium ions. The application of this method on the emission spectra obtained give the following result. The interpretation of the result obtained shows that the best dopant in concentration is to be 0.6% of orpium ions. The other interested parameter spectroscopy are also investigation. We have found the radiative transition probability, the branching ratio, the radiative lifetime as depicted in these tables. For the decay time and quantum efficiency, we choose unregistered the room temperature time resolved emission spectra of CDF2 with different concentration of RPM recorded in the spectral range of 450 to 700 nanometers and excited with 384 nanometers wavelength. We considered correct to represent only one time resolved spectra among the three concentration study. These spectra are used to extract the decay curve of yellow and the red emission. We have fitted the yellow emission decay by a single exponential curve for the curve. The measured lifetime is found to be equal to 10.15 milliseconds. All the obtained results are tabulated in this table. We found the radiative life calculated by the Gidefeld model equal for the 5D0 to 7 F1 transition and the experimental fluorescence lifetime. The quantum efficiency is found to be equal to 78%. It's good values of the quantum efficiency, and also the branching ratio are found to be equal to 80%. As conclusion, we found from the crystal produced, we have studied the spectroscopy emission and fluorescence decay time. We found a strong yellow emission at 585 nanometers, corresponding to the transition from the emitting level 5D0 to 7F1 for the 0.6% RPM ion concentration. This concentration is characterized by a strong branching ratio, long lifetime, and quantum efficiency. And thanks for your attention.